So the goal of the SVM classification is to find a hyperplane, and let's say that hyperplane is denoted by equation W transpose X is equal to 0, and we have to find a hyperplane such that the distance of the points on the two sides of this hyperplane, so the perpendicular distance of the points, so the points at the boundary, the perpendicular distance of these points from this hyperplane should be maximum. So for any given point x here, and the distance from any general, let's say the equation of hyperplane is W transpose X bar is equal to 0, and distance of any general point x from this hyperplane is given by, distance is given by absolute value of W transpose X, because W transpose X can be negative as well, but distance cannot be negative, divided by magnitude of W, which can also be written as, let's say the label of this point is y, and where y can be either 1 or -1. Let's say we are considering binary classification, so -1 refers to class 1 and 1 refers to another class. So to remove this absolute value function, we can multiply it with y, because this W transpose X would be positive for all the points where y is 1. So let's say for these points y is 1, and for these points y is 0. So for all these points W transpose X would be greater than 0, and sorry, y is -1, and for all these points W transpose X would be less than 0. So if W transpose X is less than 0, we can multiply it with -1 to make it positive. So this is the distance formula that we get, and derivation of this expression here is something I'm skipping for this video, but you can find it online at multiple places. Now the objective of SVM is to minimize this distance for all the support vectors, and what we can do is that we can look at all of these points, and we can look at the closest point, the point closest to this decision boundary. So out of all these points, I think the point closest to this boundary is this point. So we look at all the white points and we find the point which is closest to the boundary, and we maximize the distance of the point which is closest to the decision boundary. So here in case we need to maximize the distance of the green point. So basically what we'll do, we'll find the point, let's say we have n points, x1, x2 up to xn, and out of these n points we need to find the point for which this distance is minimum, y W transpose xi by magnitude of W is minimum for I is equal to 1 to n, and for this minimum point, for this xi, we have to find a W such that this distance is maximum. So this this would be yi, that is the label corresponding to the point xi. So we have to solve this optimization problem to get W, or the decision boundary, and this optimization problem can be reduced to a simpler problem as follows. So now the interesting thing to note here is that, let's say we find a solution to this optimization problem, and that solution is vector W. So if we multiply this with 2W, we'll get another solution, because this hyperplane here, let's say 2W transpose X dash is equal to 0 is same as W transpose X dash is equal to 0. So multiplying W with a scalar value would not change our hyperplane, and hence we can find any multiple of W. So if W is the answer, then KW will also be the answer. So out of all such valid answers for the W, we have to find just one of the answers. And similarly, we can see that multiplying W with K will not change the value of this expression here, because both the numerator and the denominator would be multiplied with value k, which would be equivalent to the original value. And hence, out of all these valid possible solutions, all these valued w's for the hyperplane, we are going to find that w such for which the numerator is 1. So basically what I'm trying to say is, for this point which is closest to the boundary, the value of yi into w transpose xi, let's say this point is xi, which is closest to the boundary, the value of this is 1, and we'll find one such w. And we can always find one such w because let's say the original solution of w was w dash, and yi w dash transpose xi was not equal to 1. It was equal to some alpha, some value alpha. Then we could have obtained another solution which is 1 by alpha w dash, for which yi 1 by alpha w dash transpose xi is 1, and this is also a valid solution. So basically, out of all those w's which we can find, we'll be finding that w for which this condition holds, and it will give us one answer among all the many possible answers. So now, since yi w transpose xi is equal to 1, which means for all other points, let's say yj xj, where j is not equal to I, for any other point yj w transpose xj should be greater than 1, because distance of those points is greater than the distance of those points from the hyperplane is greater than the distance of this point from the hyperplane, and distance of this point from the hyperplane would be 1 by w, and that's why distance of every other point should be greater than 1 by w, so numerator should be greater than 1, and hence yj w transpose xj should be greater than 1. And hence the problem reduces to finding a w such that distance of the point nearest to the boundary point is maximized from the hyperplane, and we have seen that distance is 1 by mod w, and we have to maximize that. But we have to also include in our constraints the assumption that the numerator is 1, and this assumption can be included by this constraint that yi w transpose xi should be greater than equal to 1 for all I belong equals to 1 to n. So for all the data points, the numerator yi w transpose xi can be either equal to 1 or it can be greater than equal to 1, but it cannot be less than 1. So this is our new optimization problem, and maximizing 1 by mod w can be also written as minimizing magnitude of w such that this condition holds: yi w transpose xi is greater than equal to 1 for all I is equal to 1 to n. And minimizing this is equivalent to minimizing the square of this. So the SVM optimization can be written in this nicely obtained format, and this expression is called SVM optimization expression for classification. I hope you like this video. See you next video.